On the evening of the 1st of November, 1943, the waters surrounding Bougainville Island witnessed a moment that would forever change naval warfare. Rear Admiral Sentaro Omori commanded his vessel, the heavy cruiser Myoko, as it cut through the darkness of the Solomon Sea. His fleet moved with precision at 28 knots. 8 warships maintained perfect formation as they navigated through the tropical night. The conditions seemed ideal for what the Imperial Japanese Navy had mastered better than any other force in the world. The air hung heavy with moisture, and visibility barely extended beyond 4,000 yards on this moonless evening. These were exactly the circumstances Japanese commanders preferred for surface combat in the dark. Omori's force represented formidable naval power. The heavy cruisers Myoko and Haguro each weighed over 13,000 tons and carried 10 8-inch guns. The light cruisers Sendai and Agano brought their batteries of 5.5-inch weapons. 6 destroyers took screening positions around the formation. Their objective was clear and direct. They intended to intercept and destroy the American invasion force that had landed at Empress Augusta Bay just hours before. The plan called for destroying the transports, bombarding the beaches, and forcing the Americans back into the sea. This wasn't unprecedented territory for the Japanese. In August of 1942, at Savo Island, a Japanese cruiser formation had surprised an Allied squadron protecting the Guadalcanal landings. Within less than 60 minutes, the Japanese had sunk 4 Allied cruisers and damaged several others, while suffering minimal damage themselves. It stood as one of the most one-sided naval victories in modern warfare, achieved entirely under the cover of darkness through superior optics, rigorous training, and aggressive tactics that the Americans simply couldn't match in low visibility conditions. That earlier battle had been fought using traditional methods, the way naval forces had engaged for centuries. Victory came from spotting the enemy first, closing to effective range, and bringing guns to bear before the opponent could respond. The Japanese had every reason to expect similar success this night. Their lookouts received the most intensive training of any navy in the world. Their optical equipment, particularly the massive rangefinders mounted on their cruisers, was exceptional. Their doctrine emphasized night combat specifically because Western navies struggled when operating in darkness. The Japanese practiced these techniques constantly, refined them through experience, and built their entire tactical approach around them. What Admiral Omori couldn't have known, as his ships raced through the tropical night, was that the fundamental nature of naval warfare had transformed in the 26 months since Savo Island. The Americans approaching from the opposite direction weren't depending on human eyes and optical rangefinders to locate their targets. They had developed something the Japanese didn't possess, something that would make centuries of naval tradition obsolete in a single night. The Americans had functional radar. At that same moment, approximately 40 nautical miles to the southeast, Rear Admiral Aaron Stanton Merrill stood in the Combat Information Center of the light cruiser Montpellier and observed green blips materializing on a radar screen. His task force, designated as Task Force 39, consisted of 4 light cruisers and 8 destroyers. On paper, his force appeared inferior to the Japanese formation bearing down on them. The Japanese had heavier guns, larger ships, and more armor. But Merrill possessed something Omori didn't have. He knew exactly where the enemy was located, how fast they were traveling, and what course they were following. The Japanese were still scanning the darkness with binoculars and rangefinders. The Americans were tracking them on electronic displays. The Battle of Empress Augusta Bay was about to demonstrate what happens when one navy fights blind while the other fights with complete information. It would become a lesson in technological obsolescence, showing how a single capability can overturn decades of tactical advantage. For the crew of the light cruiser Sendai racing through the darkness at the head of the Japanese formation, it would be their final battle. To understand what the Japanese expected that night, you need to comprehend what they had built their entire surface fleet doctrine around. The Imperial Japanese Navy had been preparing for night combat since the early 1920s, and by 1943, they believed they had perfected it. Night fighting solved several problems for Japan. The nation's industrial capacity was smaller than America's or Britain's. Japan couldn't match Western navies in total tonnage or numbers of ships. But at night, numbers mattered less. Vision mattered less. What mattered was training, discipline, and the quality of optical equipment. These were areas where Japan could compete and even excel. Japanese naval architects designed their ships with night combat specifically in mind. The heavy cruisers like Myoko mounted enormous rangefinders, some with base lengths exceeding 40 feet. These massive optical instruments could measure distances with remarkable precision in low-light conditions. They were mounted high on the superstructure to maximize the range of observation. Japanese cruiser bridges were tall, giving lookouts the best possible vantage point to spot enemy ships against the horizon. The training proved equally intensive. Japanese lookouts spent years developing their night vision. They practiced identifying ship silhouettes in darkness. They learned to detect the faint phosphorescence of bow waves at impossible distances. Senior lookouts could reportedly distinguish between different classes of warships based on subtle differences in superstructure profiles seen only in silhouette. Whether this was entirely true or partially legend didn't matter. The Japanese believed it, and more importantly, so did their opponents. Japanese optical technology was genuinely excellent. Their binoculars, particularly those manufactured by firms like Nippon Kogaku, later known as Nikon, were among the finest in the world. Their night binoculars used large objective lenses to gather maximum light, and the optical coatings were of high quality. Combined with well-trained eyes, these instruments gave Japanese lookouts a real advantage in darkness. The tactical doctrine built on these advantages was aggressive and well-rehearsed. Japanese cruiser formations practiced coordinated night attacks repeatedly. They would approach at high speed, often in column formation, to minimize the profile visible to the enemy. Once contact was made, they would turn to unmask their full broadsides and open fire at relatively close range, typically 8,000 to 12,000 yards. Their doctrine emphasized rapid, overwhelming salvos to destroy enemy ships before they could respond effectively. This wasn't just theory. At Savo Island, Japanese cruisers had demonstrated exactly what this doctrine could achieve. Vice Admiral Gunichi Mikawa's force had approached undetected, achieved complete surprise, and devastated the Allied screening force in what the United States Navy would later call one of the worst defeats in its history. The battle had lasted 32 minutes from first shots to Japanese withdrawal. 4 Allied cruisers were sinking or sunk. Over 1,000 Allied sailors were dead. Japanese casualties were negligible. The Japanese drew the correct conclusions from Savo Island. Night combat was their domain. They trained harder, refined their tactics, and entered subsequent battles with absolute confidence that darkness was their ally. American and Allied commanders drew their own conclusions. Night combat against the Japanese was to be avoided whenever possible. The United States Navy began developing new tactics, new training programs, and most importantly, new technology to counter the Japanese advantage. By November of 1943, those technological developments were about to be tested under actual combat conditions for the first time in a major surface engagement. The American response to Savo Island was not immediate, but it was comprehensive. The United States Navy recognized that fighting the Japanese at night using traditional methods was a losing proposition. American lookouts, no matter how well trained, couldn't match decades of Japanese specialization. American optical equipment was good, but not superior. The Navy needed a different approach entirely. That approach was radar. Radar itself wasn't new by 1943. The British had used it to decisive effect in the Battle of Britain. Early warning radars had given Fighter Command the information needed to intercept German bomber formations. But air search radar and surface search radar were different problems with different technical challenges. Detecting large aircraft at altitude was relatively straightforward. Detecting ships on the ocean surface and distinguishing them from wave clutter and weather returns required different frequencies and different antenna designs. The breakthrough came with the development of microwave radar, specifically the cavity magnetron. Developed at Britain's University of Birmingham in 1940, this device could generate high-frequency radio waves at centimeter wavelengths, dramatically improving resolution and reducing antenna size. The technology was shared with the United States in September 1940, when the TISARD mission delivered a cavity magnetron to American scientists. Within months, American electronics firms were developing practical applications for the Navy. The result was the SG surface search radar developed by Raytheon and first installed on United States warships in early 1942. The SG radar operated at a wavelength of 10 centimeters, giving it the resolution to detect ships at tactically useful ranges. More importantly, it could track multiple targets simultaneously, measure their range with precision, and provide bearing information accurate enough for fire control solutions. By late 1943, the SG radar was standard equipment on United States cruisers and destroyers. The antenna, a distinctive rectangular array, rotated continuously, sweeping the horizon with electronic pulses. Returns appeared on a plan position indicator display, a circular screen that showed range and bearing to detected objects. Operators could distinguish between different contacts, track their movements, and relay information to the Combat Information Center and fire control stations. The tactical implications were revolutionary. With radar, American commanders didn't need to see the enemy to know where they were. Ships could maintain radar contact at ranges far beyond visual detection, even in perfect daylight, and certainly far beyond what human lookouts could achieve in darkness. Fire control computers could calculate shooting solutions based on radar data, allowing ships to engage targets they had never actually seen with their own eyes. Admiral Merrill's Task Force 39 had been specifically organized and trained to exploit radar's capabilities. His flagship Montpellier and her sister ships Cleveland, Columbia, and Denver were all equipped with SG radar. They had practiced radar-directed night gunnery in training exercises. They had developed procedures for sharing radar information between ships, coordinating movements, and executing firing solutions based entirely on electronic data rather than visual observation. The doctrine was still being refined. Radar was not infallible. It had blind spots, particularly in rough seas where wave returns could mask targets. It required skilled operators to interpret the displays correctly. Equipment could malfunction or be damaged in combat. But when it worked, radar provided information that was simply unavailable through any other means. It allowed commanders to see the battle space in its entirety, to track enemy movements in real time, and to position their forces for maximum advantage. On the night of November 1st, 1943, these two doctrines, one perfected over decades and one barely 2 years old, were about to collide in the darkness off Bougainville. The Japanese were coming north at high speed, confident in their night-fighting superiority, relying on methods that had brought them victory before. The Americans were waiting, watching the Japanese approach on radar screens, preparing to fight a battle in a way that had never been done before. The question wasn't whether the Americans had a technological advantage. The question was whether they could translate that advantage into tactical success before Japanese guns found their range. The SG radar aboard Montpellier was a Model SG-1 manufactured by Raytheon. The system consisted of a transmitter producing 50 kilowatts of peak power at a wavelength of 10 centimeters, an antenna array measuring approximately 4 feet by 2 feet that rotated at 15 revolutions per minute, and a plan position indicator display in the Combat Information Center. The effective detection range against a cruiser-sized target in good conditions was approximately 30,000 yards, roughly 15 nautical miles. Against smaller targets like destroyers, the range decreased to perhaps 20,000 yards. The radar operator sat before a circular display screen 12 inches in diameter. The center of the screen represented the radar antenna's position, which was also the ship's position. Concentric circles marked range increments, typically graduated in thousands of yards. A bright sweep line rotated around the screen in synchronization with the antenna rotation, painting new information with each revolution. When the transmitted radar pulse struck a solid object and reflected back, the return signal appeared as a bright spot or pip on the screen at the appropriate range and bearing operating. The SG radar required skill and experience that American radar operators were still developing in late 1943. The operator had to distinguish genuine contacts from false returns caused by weather, sea clutter, or equipment anomalies. Rain squalls could appear as large amorphous blobs on the screen. Heavy seas produced clutter near the center of the display where waves reflected radar energy. The operator needed to recognize these patterns and filter them out mentally while identifying actual ship contacts. The radar information flowed to the Combat Information Center, a compartment deep within the ship's hull, where officers plotted tactical information on large plotting tables. Each radar contact was assigned a designation and tracked manually on the plot. Officers calculated the contact's course and speed based on successive radar positions. This information was relayed to the bridge and to the fire control stations where gunnery officers prepared firing solutions. The fire control system itself represented another technological advantage. American cruisers used Mark 8 fire control radar for main battery gunnery, a separate system from the SG search radar. The Mark 8 provided precise range information for fire control computers. These computers, electromechanical devices weighing several tons automatically calculated the required gun elevation and deflection based on target range, bearing, speed, and the ship's own motion. Gunners cranked their guns to match pointers that received electrical signals from the computer. When the pointers aligned, the guns were aimed correctly for the current solution. The Japanese had nothing comparable. Their fire control relied on optical rangefinders and mechanical calculators. A Japanese cruiser's main battery director included a massive coincidence rangefinder, an optical instrument that measured distance by aligning two images of the target viewed through telescopes at opposite ends of a long baseline. The rangefinder operator adjusted controls until the two images coincided perfectly, and the mechanism translated this adjustment into a distance measurement. This system worked remarkably well in daylight or under good visibility conditions. Japanese rangefinders were accurate and their operators were well trained. But at night, the system's effectiveness depended entirely on being able to see the target clearly enough to align the images. In complete darkness, or at extended ranges, this became difficult or impossible. The Japanese compensated by using searchlights to illuminate targets during the final stages of an attack. But searchlights also revealed the searching ship's position to every enemy vessel in range. Japanese fire control computers were mechanical devices that calculated firing solutions based on manual inputs from the rangefinder and target-bearing measurements. They were slower than American electromechanical computers and less capable of handling rapid target maneuvers. More importantly, they couldn't receive electronic input from radar because Japanese ships generally lacked fire control radar. The disparity extended to doctrine and organization. American ships had dedicated combat information centers with officers specifically trained to manage radar information and tactical plotting. Japanese cruisers had no equivalent spaces. Radar information, when available at all on Japanese ships equipped with early air search radars, went directly to the bridge where the commanding officer and his staff had to process it along with all other information while simultaneously directing the ship's movements and fighting the battle. Admiral Merrill's battle plan exploited these advantages systematically. His 4 cruisers would operate in column formation, steaming at 28 knots. The destroyers were divided into 2 divisions, positioned on the flanks where they could launch torpedo attacks or screen against Japanese destroyers. The cruisers would rely on radar to detect the Japanese force while remaining undetected themselves. Once contact was established, Merrill planned to maneuver his column to maintain optimal firing positions while using radar to track Japanese movements continuously. The plan required precise coordination. All 4 cruisers needed to turn together to unmask their broadsides simultaneously. Fire control needed to distribute targets to avoid multiple ships engaging the same Japanese vessel while leaving others unengaged. The destroyers needed to coordinate their torpedo attacks with the cruiser gunnery to maximize confusion in the Japanese formation. Every element of the plan depended on maintaining accurate radar tracking of the Japanese force while preventing the Japanese from gaining similar information about American positions. At 23:45 hours on November 1st, Montpellier's SG radar detected multiple contacts bearing 315 degrees true, range 31,000 yards. The Japanese force had been located exactly where intelligence had predicted they would be. The radar operator reported 7 distinct contacts, later amended to 8 as the returns resolved more clearly. The Combat Information Center began tracking the contacts, calculating their course as 130 degrees at 28 knots. The Japanese were heading almost directly for the American transport area at Empress Augusta Bay. Admiral Merrill had his information. The enemy was 15.5 nautical miles away, moving at high speed, completely unaware that they had been detected. The Americans had achieved exactly what Japanese doctrine said was impossible. They had found the enemy first at night at a range where visual detection was utterly impossible. Now they needed to convert that information advantage into tactical success. At 23:50 hours, Admiral Merrill ordered his task force to increase speed to 30 knots and alter course to intercept the Japanese force. His cruisers were still invisible to Japanese lookouts, but the radar picture showed the 2 formations converging. The range decreased steadily. 28,000 yards, 25,000, 22,000. Still no indication that the Japanese knew American surface ships were in the area. Admiral Omori aboard Myoko had received reports of Americans' ships near Empress Augusta Bay, but his information suggested they were transports and their destroyer escorts, vessels that would flee rather than fight. His force had been detected by American aircraft earlier in the day, but he had no reason to believe American surface combatants were positioned to intercept him. His lookouts strained their eyes in the darkness, searching for American transports against the dark mass of Bougainville Island. They saw nothing yet. That was normal. They wouldn't expect to detect targets until they closed to perhaps 10 or 12,000 yards in these conditions. At 01:30 hours on November 2nd, the range had decreased to 20,000 yards. Merrill ordered his column to turn to course 270 degrees, heading almost due west. This maneuver positioned his cruisers to cross ahead of the Japanese force, the classic naval tactic of crossing the T. Every gun on his 4 cruisers would bear on the Japanese ships, while the Japanese could only return fire with their forward guns until they turned to unmask their broadsides. It was the ideal tactical position, achieved without the Japanese having any indication of American presence. Aboard Sendai, the light cruiser leading the Japanese formation, lookouts continued their vigil. Captain Toshio Kobayashi stood on the bridge, binoculars raised, searching the darkness ahead. Sendai was designed for this role. Fast, maneuverable, equipped with excellent optical equipment and an experienced crew. She displaced 5,500 tons, mounted 7 5.5-inch guns, and could make 35 knots. Her lookouts were among the best in the fleet. They should detect any American ships long before the Americans detected them. They detected nothing. At 01:47 hours, with the range down to 18,500 yards, Merrill ordered his cruisers to open fire. The order was transmitted electronically. No searchlights illuminated targets. No visual confirmation preceded the firing order. The fire control radars had locked onto specific Japanese ships. The fire control computers had calculated solutions. The guns were already trained on targets. The gun crews could not see and would never see with their own eyes. Montpellier's main battery consisted of 12 6-inch guns in 4 triple turrets. At 01:48 hours, all 12 guns fired simultaneously. The night erupted with a brilliant flash visible for miles. Seconds later, Cleveland, Columbia, and Denver added their guns to the bombardment. 48 6-inch guns firing in coordinated salvos, sending over 2 tons of steel screaming through the darkness toward Japanese ships that still had no idea American cruisers were even present. The first salvos fell around Sendai. Enormous columns of water erupted near the ship as shells struck the sea. Some rounds hit. 6-inch armor-piercing shells traveling at 2,800 feet per second struck Sendai's thin hull plating and kept going, passing completely through the ship before exploding on the far side or continuing into the ocean. The cruiser shuddered with the impacts. Men were thrown from their feet. Equipment was torn from mountings. On Sendai's bridge, the reaction was not fear or panic, but complete bewilderment. They were being shelled at night from a direction where no enemy ships had been detected, at a range where visual detection should be impossible. The brilliant gun flashes from the American cruisers were now visible, appearing suddenly out of darkness at an impossible distance. The mathematics didn't work. If they could see the gun flashes now, the American ships must be at least 15,000 yards away, probably farther. But how had the Americans known where to shoot? How had they achieved such accurate fire without searchlights? Without any indication, they had even detected the Japanese force. Captain Kobayashi ordered an emergency turn to starboard, trying to unmask Sendai's full broadside and return fire. The light cruiser heeled hard as her rudder went over, but the American fire control had tracked the turn on radar. Fire control computers recalculated instantly. The next American salvos adjusted for Sendai's maneuver, following the ship through her turn. More shells hit. The forward turret was struck and disabled. Fires started amidships. The bridge structure was hulled repeatedly. Admiral Omori, several thousand yards behind Sendai in Myoko, faced his own crisis of comprehension. His lead ship was under accurate gunfire from an enemy force that shouldn't be there. firing from ranges that shouldn't allow accurate shooting, hitting targets in darkness that traditional doctrine said should be undetectable. His carefully rehearsed night attack plan assumed the Japanese would detect the enemy first, close to effective range, and open fire from a position of advantage. Instead, the Americans had ambushed him, achieving surprise through some method he didn't understand. Omori ordered his heavy cruisers to turn toward the gun flashes and return fire. Miyoko and Haguro began launching salvos from their 8-inch guns, but they were firing at visible muzzle flashes, not at actual ship positions calculated by fire control equipment. The heavy shells, each weighing over 250 pounds, fell in patterns around the American cruisers, but achieved few hits. The American ships were constantly maneuvering based on radar information, turning to avoid torpedo attacks from Japanese destroyers, adjusting position to maintain optimal firing range. The Japanese were shooting at where the Americans had been seconds earlier, not where they were now. Sendai absorbed tremendous punishment in the opening minutes of the battle. American 6-inch shells continued to strike her hull and superstructure. Each hit created catastrophic damage on the lightly armored cruiser. The Japanese ship had been designed to dish out punishment, not to receive it. Her armor, adequate against destroyer gunfire and shell fragments, offered no meaningful protection against direct hits from 6-inch armor-piercing projectiles. At 01:55 hours, a salvo from Montpellier struck Sendai's engineering spaces. The shells penetrated the thin deck armor and exploded among the boilers and turbines. Superheated steam at 600 degrees Fahrenheit exploded through the compartments, killing every man in the engineering spaces instantly. The ship's power failed. The lights went out. The turrets stopped responding to training orders. Sendai was dead in the water, still afire, settling by the bow. Captain Kobayashi stood on what remained of his bridge and understood with perfect clarity that his ship was doomed. They had sailed into battle expecting to use their superior night fighting techniques against inferior American forces. Instead, they had been detected at impossible ranges, engaged before they could return effective fire, and hit repeatedly by an enemy they still couldn't see clearly. The Americans had some capability the Japanese didn't possess, some technology that allowed them to shoot accurately in complete darkness at extended ranges. Sendai's surviving crew abandoned ship at 02:10 hours. The cruiser remained afloat, burning, until approximately 04:30 hours when she finally rolled over and sank. Captain Kobayashi went down with his ship, maintaining the tradition of Japanese naval commanders. Over 300 members of Sendai's crew of 500 men were dead or would die in the water. Some were killed by the shell hits. Others died in the fires. Still others drowned when the ship sank. Some survivors were machine-gunned in the water by American destroyers during subsequent phases of the battle, a grim reality of night combat where distinguishing friend from foe was nearly impossible and stopping to rescue enemy survivors could be fatal. The battle continued for several more hours, evolving into a confused melee as Japanese destroyers attempted torpedo attacks and American destroyers countered with their own torpedo runs. But the fundamental character of the engagement had been established in the first 15 minutes. The Americans could track Japanese ship movements continuously on radar. They could maintain firing solutions even as targets maneuvered. They could coordinate the fire of multiple ships against single targets, or distribute fire effectively across multiple targets. The Japanese were fighting the traditional way, trying to close range, trying to achieve visual contact, firing at gun flashes and estimated positions. Admiral Omori withdrew his remaining ships at approximately 02:30 hours, ordering a retirement toward Rabaul. He had lost one light cruiser sunk. The destroyer Hatsukaze sunk by American destroyers during a confused engagement and had sustained damage to several other ships. The Americans had damaged one destroyer, Foot, which lost her stern to a Japanese torpedo, but survived. In terms of material losses, the battle was not catastrophically one-sided, but in terms of psychological impact and tactical demonstration, Empress Augusta Bay was devastating. The Japanese Navy had entered the battle confident in their night-fighting superiority. They had exited it having been ambushed, outfought, and driven off by an enemy using methods they didn't understand, and capabilities they couldn't match. The sacred doctrine of night surface combat, perfected over decades, practiced religiously, and validated by victories like Savo Island, had been rendered obsolete by American radar. Japanese after-action reports reflected confusion and uncertainty about what had actually happened. How had the Americans detected them first? How had they achieved such accurate fire at such extended ranges? Some Japanese officers theorized that the Americans must have had submarines or aircraft providing targeting information, not understanding that surface search radar could perform that function. The concept that a ship could electronically see other ships at 15 or 20,000 yards was not something Japanese naval doctrine had prepared them to encounter. The fundamental irony was complete. The Japanese had developed night combat doctrine specifically to offset American material advantages. They had trained harder, developed better optics, and built tactical systems around capabilities where they could compete. But technology had shifted the competition to a different arena entirely. American industrial capacity had produced not just more ships and more guns, but new capabilities that changed the rules of engagement. Radar didn't just provide an incremental advantage. It provided categorical superiority in night combat, turning Japanese expertise and training into irrelevant skills, like being the world's best archer in the age of gunpowder. The survivors of Admiral Omori's task force limped back to Rabaul over the following days. Damage reports were compiled, casualty figures tallied, and operational assessments written. The loss of Sendai and Hatsukaze represented significant material losses, but the Imperial Japanese Navy had suffered worse defeats and recovered what couldn't be so easily. Recovered was the psychological foundation of Japanese naval doctrine. Senior officers at Combined Fleet Headquarters studied the battle. Reports from Empress Augusta Bay with growing concern. The accounts from surviving officers described American gunfire of impossible accuracy in total darkness. Ships engaging at ranges where visual detection should have been impossible. Coordinated fire from multiple vessels against specific targets, without searchlights or visible communication. The pattern suggested some technological capability beyond normal optical equipment. Japanese intelligence had known the Americans possessed radar. Japanese ships had encountered American air search radar, and a few Japanese vessels were being fitted with their own early warning radar sets for detecting aircraft. But the concept of using radar for surface search and fire control had not been fully appreciated. Japanese radar development had focused on air defense, matching what they understood the British and Americans were doing. The idea that radar could replace optical rangefinders and visual observation for surface combat represented a conceptual leap that Japanese naval planning had not made technical intelligence. Officers examined captured American radar, equipment from downed aircraft and damaged ships. They studied the principles of operation, the frequencies employed, the antenna designs. Japanese engineers understood the physics. They could in theory build similar systems, but understanding a technology and deploying it effectively across an entire fleet were vastly different challenges. By late 1943, Japan's industrial capacity was already strained by years of war. Shipyards were struggling to replace combat losses. Aircraft production consumed resources that might otherwise go to electronics manufacturing. The nation's technological base, while sophisticated, was smaller than America's and lacked the slack capacity to rapidly incorporate new systems into existing designs. More fundamentally, Japanese naval doctrine had to change, and institutional change is always slower than technological change. The entire tactical framework of night combat, the training programs for lookouts, the design philosophy of cruiser bridges and optical equipment, the positioning of searchlights and illumination procedures, all of these were built around assumptions that radar invalidated, teaching an entire navy to fight differently, to trust electronic instruments over human eyes, to abandon techniques that had brought victory in the past, required time that Japan didn't have. Admiral Omori never commanded another major surface force. He was not formally punished for the loss at Empress Augusta Bay. Japanese Naval Command recognized that he had faced an unexpected technological disadvantage, but his career had effectively ended. His practical experience of night combat had been rendered obsolete by circumstances he couldn't have anticipated. The Japanese Navy continued to attempt night surface actions in the following months, most notably in the Battle of Cape St. George later in November 1943. The results were similar. American destroyers using radar to track Japanese destroyer forces ambushed and sank 3 Japanese destroyers without loss. Again, the Americans detected the Japanese first, achieved surprise, and coordinated their attacks using electronic information rather than visual observation. Japanese tactical responses evolved to account for American radar, but these were defensive adaptations rather than solutions. Japanese ships began using more frequent course changes to complicate American fire control solutions. They employed smoke screens more extensively to break radar locks, though this also degraded their own ability to observe targets. Some Japanese commanders adopted more cautious approaches, avoiding night surface combat when possible. But caution is not a winning strategy in a war where the enemy controls more resources, produces more ships, and can afford to be aggressive while you cannot. The psychological impact on Japanese crews was profound. Sailors who had trained for years in night combat techniques discovered their skills were irrelevant. The pride that came from mastering difficult optical rangefinding or developing exceptional night vision meant nothing when the enemy could see you electronically before you saw them visually. Morale suffered not from simple defeat, but from the realization that the contest itself had changed to one where Japanese advantages no longer applied. Japanese destroyer and cruiser crews going into subsequent battles knew they were technologically outmatched. They knew the Americans would detect them first, would track them continuously, and would coordinate attacks that Japanese forces couldn't match. Courage and training couldn't compensate for this fundamental disparity. Men still fought, still followed orders, still executed their duties with the discipline and skill Japanese naval service demanded. But they fought with the knowledge that victory was unlikely, and that they were employing tactics the enemy had already countered with technology Japan couldn't match in time or quantity. For the United States Navy, Empress Augusta Bay validated both the technology and the tactics built around it. Radar-directed night combat worked. The investment in research, development, and fleet-wide installation of search and fire control radar had produced decisive tactical advantages. The Combat Information Center concept, bringing radar operators and tactical plotting into a dedicated space, had proven effective. The integration of radar data into fire control solutions had enabled accurate gunnery at ranges and in conditions where optical systems couldn't function. Admiral Merrill received praise for his handling of the battle, but he was careful to credit the technology and the training his crews had received. In his after-action report, he emphasized the critical role of radar, noting that without it, the engagement would have been far more difficult and the outcome uncertain. He recommended continued emphasis on radar training for all officers and enlisted personnel, and he suggested tactical improvements based on lessons learned during the engagement. The Navy's Bureau of Ships and Bureau of Ordnance took note. Production of SG radar sets increased. New variants were developed with improved range and resolution. Fire control radar continued to be refined, with later models offering better tracking capabilities and faster data processing. Every new cruiser and destroyer launched from American shipyards came equipped with the latest radar systems as standard equipment. Older ships underwent refits to install or upgrade their radar outfits. Training programs expanded to match the technology. Radar schools were established at shore installations where operators learned to interpret displays, distinguish contacts, and manage equipment. Combat Information Center teams practiced coordinating information flow and tactical decision-making. Gunnery officers learned to trust radar data even when it contradicted visual observation or traditional range finding. The cultural shift from seeing with eyes to seeing with electronics took time, but the Navy invested that time because the results justified it. The tactical advantages extended beyond night combat. Radar allowed American ships to track targets in poor weather, in rain squalls, in fog, conditions that rendered optical equipment nearly useless. It provided early warning of approaching enemy forces, giving commanders time to position their ships advantageously. It enabled effective air defense by detecting incoming aircraft at ranges where visual spotting was impossible. It revolutionized navigation, allowing ships to fix positions relative to coastlines and known landmarks, even in zero visibility. By 1944, American naval superiority in the Pacific was overwhelming, and radar was a significant component of that superiority. Japanese surface forces largely avoided major engagements, recognizing they couldn't win. When forced to fight, as in the Battle of the Philippine Sea in June 1944 or the Battle of Leyte Gulf in October 1944, Japanese ships were systematically destroyed by American forces that could coordinate their movements, concentrate their firepower, and execute complex tactical maneuvers that would have been impossible without radar. The technology also changed American naval architecture and operational concepts. Cruisers and destroyers were designed with larger superstructures to mount radar antennas and house combat information centers. Bridge layouts evolved to integrate radar displays with traditional navigation and ship control stations. Communication systems were enhanced to share radar information between ships, creating a networked tactical picture that gave American commanders unprecedented situational awareness. The differential in capability wasn't subtle. American commanders routinely had accurate information about enemy positions, courses, and speeds, while Japanese commanders operated with fragmentary information gathered visually or from radio intercepts. American ships maneuvered based on complete understanding of the tactical situation, while Japanese ships maneuvered based on incomplete information and assumptions. The result was a systematic American advantage in virtually every surface engagement from late 1943 through the end of the war.